because of my plotting. Resolution is no good. You follow? So this point supposedly should, go to minus infinity in dB. And if you to plot it in terms of absolute value, then this is what you see in your sinc or function that appear as a sinc function. This is what you should see. If this is not plotted vertically in dB scale, you should see that this corresponds to, this is absolute gain, this is your zero value. And if let's say this is the value n. So these are known as null. So in the sinc function is basically zero crossing of your horizontal axis. So now we have a null here, there is another null here. For this case, what you can see that there is no null at the 2 inferior direction. So this one is clear cut. 1, 2, 2 plus 1 gives you 3. This one, 1, 2, 3, 4, 5, 6, 6 plus 1 gives you 7. But for nulls occurring at the 2 inferior directions, you have to remember that when you count this null, you should not count the other one. Because this belongs to the range of 180 degree to 365.99999 degree. You follow? From 0 degree, you should count up to 179.9999999 degree. You should not include 180 degree. 180 degree is the next cycle. You see a lot of similarity in your array theory with that of your signal theory or filtering theory. Exactly the same. You see, just now we mentioned, maybe sidetrack a little bit. We mentioned that if you signal from the inferior direction, signal will be cancelled. In terms of FR filtering, what do you have? If this is your sampling interval, and if your sampling interval corresponding to what? How? Well, if your sampling rate is 2 times of your signal frequency, then this will be corresponding to what? Well, the sampling interval corresponding to your 2 times of the sampling rate. So therefore, well, the phase shift is 180 degrees. Exactly the same thing. And you can actually see this as a kind of FR filter, but in physical space. You see here, signal coming in from this, across from this direction across the array aperture, there is always a time delay, right? So when you draw your filter structure, this is what you see, right? So that is your sampling interval, right? This is your FR filter. So this is your FR filter, and this is your sampling interval. When signal is propagating across the so-called step delay line, this is your transversal filter or FR filter. When signal is propagating through this, it's going to be delayed, right, by this sampling interval. You follow? This sampling interval corresponds to the time propagation through this half wavelength distance. Half wavelength is 180 degree phase shift. If this is your sampling interval corresponds to your Nyquist sampling rate, then this corresponds to your 180 degree phase shift. So exactly the same thing. And in this case, the filter coefficient should be all 1 for the case of your uniform linear array. Okay, now here, what happens if your element spacing D is being varied? Well, you can see that the aperture is going to change, and you end up with, if the inter-element spacing is more than lambda, or you see more grating loops. Alright, so here spacing is 2 times of lambda, so you can see that you have a lot of grating loops. Beside the beam at the broad side, you have a lot more grating loops. So there is a problem if you don't control the inter-element spacing correctly. Now, if the element is non-isotropic, so this is something that we have mentioned just now, the pattern multiplication theorem will come into picture. Remember, just now we said that the overall linear array response is given by the array factor multiplied by the beam pattern of your individual antenna element. Alright, so here this is the beam pattern of your individual antenna, and this is the array factor. The overall response is given to be this. So how this is obtained? Basically, you multiply the amplitude of the two graphs. So which means that if you turn this instead of dB into absolute value, you multiply with the response in terms of absolute value. If the two beam patterns are expressed or drawn in terms of gain in dB, then at this point, if you have a -6 dB, and over here we have about -10 dB, then the overall response at this angle, 20 degree, will be -6 plus -10, and that should give you about -16. Of course, my estimation wasn't accurate, so it is around -15 or -16. This should be -15 to -16. Alright, so that is how we obtain the overall beam pattern, and that is the array factor multiplied with the individual array element beam pattern. That is so-called pattern multiplication. Okay, now this is basically just to illustrate to you, theoretical derivation in real life pattern. An ideal linear array may give you a beam pattern that looks like this, but when you implement it and measure it, it may end up to be something different, not exactly the same, and that is so-called perturbation. Perturbation may be in terms of sensor position. It may be perturbation in terms of the individual gain phase response of your individual element. Alright? So, what we are trying to say here is, when the array is being designed, geometry being fixed on paper, the response being calculated theoretically, but when you implement it with your real antenna elements, and when you measure the response of the linear array, it is 100% not going to be the same as your theoretical beam pattern. We can always say that it's 100%, not the same. And that is because of the perturbation. More critically is the position. So now, I have a linear array. I need to mount the monopole antenna along a straight line, right? One here, next element here. You say, okay, half wavelength, right? So we can actually mark up the position and then mount the antenna accordingly. But this mounting is going to give you error. So supposedly the half wavelength may be, say, 1 meter. The mounting may be occurring at a distance 1.01 meter. So that is called perturbation. Supposedly this antenna should be located at the reference point at a distance of 1 meter, or you may end up at the position 1 meter and 1 millimeter. 1 meter plus 1 millimeter. So the 1 millimeter is the perturbed distance error. You follow? Next distance may be supposedly at 2 meter distance, but you may end up at 1.999 meter location. You follow? So there is perturbation along this dimension. There may be perturbation in the other dimension as well. So there is a lot of possibilities. Alright? And as a result, you find that the beam pattern will not be the same as the theoretical beam pattern. And that is called perturbation or errors. So perturbation may be in terms of physical mounting, it may be in terms of the gain, the electrical gain and phase of the individual element. So that is called gain phase perturbation. Well, gain phase perturbation is because of your defect or imperfection in your manufacturing process of your antenna. The material used may not be homogeneous, may not be, the conductivity, the conductivity or whatever may not be consistent. Also, there's a lot of possibilities. Okay, so with that, any question before we move on to the tutorial question?